Today, when someone says Pangaea, we often associate it with a supercontinent, perhaps because it quite literally translates to all land.
However, for someone not born in this century, it is quite absurd to think that the Earth was assembled into a large single landmass 300 million years ago. Enter Alfred Wegener. He proposed that the continents were once connected because of the way they fit, fossil evidence, and similar rock types and paleoclimates across continents.
While Wegener was correct about most of his observations, he was unable to explain the reason behind this continental drift.
Later, the theory of plate tectonics was introduced, which is not quite the same as continental drift. See, continental drift suggests that only the land masses were moving. The theory of plate tectonics states that the lithosphere, including the continental and oceanic crust, is divided into plates that basically float on the plasticky upper mantle. But this theory was still groundless, so one of the pieces of evidence to support it was paleomagnetism and seafloor spreading. When the seafloor was mapped during World War II, on either side of a mid-ocean ridge was a pattern seen in the rocks. The rocks showed high and low intensity magnetic fields symmetrically on both sides of the ridge. This pattern is observed because rocks can record the direction of the Earth's magnetic field. This field can undergo reversals where the current field is normal polarity, and when it's flipped, it's reverse polarity. How does this magic happen, you ask? Magnetite, a ferromagnetic mineral. Rocks that have magnetite can acquire thermoreminant magnetization. When lava cools to form rocks and the temperature of the rock drops below the Curie temperature, the rocks record the magnetic field direction at that moment. The Curie temperature is essentially a threshold above which the grains of magnetite are not aligned in a single direction.
Analyzing rocks to collect paleomagnetic data is quite useful, you see, because the direction of the poles collected from different rocks on different continents from a certain geologic period can help geoscientists reconstruct the position of continents.
So let's take a look at inclination and declination. Due to the geomagnetic field not being that of a perfect bar magnet, there are a few inconsistencies that lead to the poles not coinciding with the geographic poles. Thus, declination gives us the angle between the geographic north and the geomagnetic north pole. Inclination, or the dip, is the angle between the geomagnetic field and the horizontal plane. The inclination, when found in the lab, can then be used to find the precise latitude of the region of land that was sampled. To do this, we use the dipole equation, where if we input the inclination, we can easily calculate the latitude.
So in my opinion, it's very important to study paleomagnetism because combine inclination and declination with radiometric dating of rocks, and that is precisely how we know the exact time of existence and location of Pangaea and how we are now reconstructing Rodinia, Pangaea's billion-year-old predecessor.